So our next speaker is going to be Stefano Soatto from UCLA. He's in the computer science department. Stefano is an expert in control theory, computer vision, and I guess more generally he's interested in problems that combine sensory information with estimation, learning, and control.
Thank you, Paul. Thank you all for coming. And so this talk is about differential learning, which is another name for deep learning. And so if you talk about deep learning, you have to show at least one picture of a cat. So I'll do it at the outset. Slightly less cute, perhaps, but this is a cat with cataract. Sometimes they're born that way. This is a congenital cataract. And these are Hubel and Wiesel, who in the 60s conducted a number of groundbreaking experiments down the street at Harvard. And I want to tell you about one of them. Okay, so what they did is they took cats that had congenital birth defects, like cataract, visual impairments, or they put an eye patch on them for a certain period of time. And after a certain period of time, 1 day, 2 days, 3 days, 5 days, 100 days, they removed the patch and let the cat roam free, or they corrected the cataract. They removed the cataract. So what they observed is something like this. So they measure, after a while, the visual acuity of the cat, how well the cat could see, as a function of how early you remove the deficit. Okay, so for instance, if you remove the deficit at birth, forget about the units here, they don't matter, but this is how well the cat could see. And the green curve here is how the normal cat learns to see and eventually reaches this type of performance. So if you remove the deficit immediately, the cat eventually learns, develops a normal vision. But if you remove it after 10 days, 20 days, 100 days, 200 days, no matter how much time the cat has available, it will never develop a normal vision. Okay? So these are well-known phenomena in biology that are called critical learning periods. They affect all sorts of species and skills, from some birds to humans also. So this was my child. When he was born, he wasn't smiling. And we discovered that he needed glasses. And had we not corrected him early, he would never have developed a normal vision. There's quite a number of people who are amblyopic because of that. So the explanations for critical periods are exquisitely biological. So they have to do with neuronal plasticity. I'm not a neuroscientist, but my understanding is that as you age, you lose neuronal plasticity, and then therefore, what you haven't learned in the early phases of postnatal development, you never learn. So that's why you cannot teach an old dog new tricks. This is a neural network. Okay, it doesn't age. Knows nothing about biology. Its connectivity is fixed at the outset. There's no neuronal plasticity. So if you were to try to replicate this experiment of Hubel and Wiesel, you would not expect anything at all like that, right? So how do you do an experiment like that? Well, so you can take a data set of images, and you can simulate a cataract by showing the network for the first few epochs slightly blurry images. Okay, these are CFAR images, and it's a classification task. You could take images of the optocharts that you go and look at when you go to the optometrist. Okay, so you take the network and training for a few epochs using slightly blurry images with the task of classifying CFAR images, and then you switch to normal images and you let the network learn for however long you want. Okay, so asymptotically, okay, the loss function is the same of training CFAR digits. So what changes is the transient, okay? And what you observe if you do that experiment is something like this, okay? So what you see is performance on CFAR. State-of-the-art networks nowadays reach about 95%. So if you never show blurry images, you reach that. But even if you train with 20 or 40 or 60 epochs of blurry images, and then you let it go for 200 epochs or more, eventually you reach a performance which is about 18% error instead of 5% error. So it's manifold the error. So you never recover, okay? So this is bizarre because, again, asymptotically, the loss function you're optimizing is the same as the outset. I'll slice this experiment in another different way. So now imagine you're born and you need glasses, like my son. But for a period of 40 epochs, I take off your glasses and then I put them back on. And now I plot the deficit you ultimately register as a function of when I apply the deficit, okay? So at the beginning, you have no deficit, then you have a deficit for 40 epochs of training, and then you correct the deficit. And what you see is this very characteristic curve where the early stages of training, if you do it at the beginning, the first 40 epochs, it's all chaotic, so nothing much happens. But really, there is this critical period where if you mess with the data, you never learn properly. Okay? This is the same plot for cats. Okay? This is actually a done post-mortem where they measure functional connectivity in V1. And so you see this very characteristic red curve. So keep that in mind because I'll come back to that. Okay? So what does this have with dynamics and control? So essentially the point that Alessandro Achille and Matteo Rovere made here is that the transient of learning in deep networks is literally critical. If you mess with that, it doesn't matter how long you go, you never learn properly. Okay? Which is odd, if you ask me. And so I'd like to understand that a little bit. So I would like to talk about the dynamics of information while training a deep network, which requires me to, first of all, say, what does it mean to learn? So for this talk, a learning task is a data set. Okay? If you take classified, supervised classification, the data set specifies what the task is. You don't know anything else but that. Okay? So inputs and outputs, images and classes, or take your favorite, that's the task. Now, at the end of training, whatever information was there in the task or in the data set is in your weights. That's all you have left. Right? So it seems important to understand how to measure information in the weights, which is non-trivial because the weights are a fixed vector, and the network after training is a deterministic function, but I'll come to that. So, but amuse me for a second and pretend we knew how to measure this information. So if you can hypothesize how that would go during training, you would imagine that as you learn the amount of information in the weights of a network, or the amount of information the model knows about the task, grows and maybe reaches an asymptote with diminishing return. But if you actually measure that, and how you measure information in tens to hundreds of millions of dimensions requires different talk, you observe something like this. Okay, this is, again, bizarre. So what you observe is that in the first few epochs of training, the network acquires a lot of information, okay, very rapidly, and then at some point it starts throwing it away. So it starts forgetting, okay? This kind of goes against my grain because one of my mentors used to say that his mother always told him to never throw away information. But here, it appears that not only it happens, but it's actually beneficial. So what you see in the green curve here is test accuracy. So test accuracy keeps going up even as you are throwing away information, which is counterintuitive. Okay? Now, what does it have to do with cats and cataract? So if you plot the sensitivity curve to critical periods, which I shown in red earlier, of course, it's on a different scale, so you need to resize it, and overlay it, you get something like that, which is interesting. Okay. So obviously, there is dynamics in information during learning. We like to understand that. And can we control that dynamics? Yes. When you're training a deep network, it's very easy to control information. You can just inject noise into during the training process. So you can control it all the way to maximal information, you do nothing, all the way to zero information where you inject so much noise that you disrupt everything. And you have one knob per weight, if you wish, 1 million knob, or one for the entire network, or one per layer, or one per filter. So it's your choice. So you have complete control. So if you want to control information in a network, how would you do so? What is the criterion for doing that? Because a learning task is specified by the training set, but the desiderata for the control task or the goals pertain to the test set, which you haven't seen. You don't care to be invariant to nuisance variability affecting data that's sitting in your memory you'll never see again. You care to learn a representation that is sufficient as informative as the data and invariant to nuisance variability affecting future data which you haven't yet seen. So how do we formalize that? And how do we formalize in a way that allows us to predict whether we'll be able to solve a learning task without actually doing what we do today, which is when we try it and see it. Okay? So I'll organize the rest of my talk in 15 minutes in 3 parts. In the first, I'll talk a little bit about information in the weights. There's a lot of details and nuances. They're in the papers, they're on archive, but I'll try to give you the gist. And there is this information Lagrangian, which is what you would like a deep network to optimize, even though it's not what it does. Now, that all pertains to the past. All the training knows is about the past, but you would like to guarantee properties of representation of test data you have never seen. And so I'll show that there is another Lagrangian that is different from the one of the weights, and the two are related by the emergence bound that I'll talk about. And finally, I'll talk about how to actually try to connect the two, and I'll argue that SGD is essentially controlling the amount of information in a feedback, and that allows us to connect the notion of information to complexity and reachability of tasks. Okay, so what does information in a deep neural network mean? So you have a data set. That's a bunch of data stored in memory. You have a goal, which is that of learning or approximating some type of model of the real conditional distribution from which the data is drawn, but you don't know the distribution, so that's your goal. And in the middle, you estimate some weights, which is a fixed vector of parameters. And you do so by minimizing what's known as the empirical cross entropy for the case of classified or supervised classification, which is a sum over the samples of essentially the empirical log likelihood. And I'll call that H sub P and Q, in the sense that it's a function that depends on the true distribution P through the sample. You have n of them, so they're finite. Q, which is your model, and it's a function of the data set that you optimize with respect to the weights. Okay? So how do you measure the information in the weights? The weights are a fixed vector. Okay, you could measure coding length. You pick a code or a prior, and you look at the posterior and measure the coding length. But that would not be very meaningful for deep networks, because as you know, once you've trained a network, there are some weights that you can change however you want, and it has zero effect on the input-output behavior of the network. So you would argue that that weight contains zero information. So why should you use bits to encode it? You can just set it to 0 or make it random. You don't care. On the other hand, suppose that there is a weight that changing it, the least significant bit, makes a huge difference in the discriminant. Then you say that network encodes a lot of information. I want to encode it with a large number of bits. So really what matters is not the coding length of the weights, but the effect of that on the loss, on empirical cross entropy. And so if you imagine pinning this at the minimum, then the second term in this Lagrangian essentially measure the unit cost in bits, so the cost in bits of a unit of loss through the parameter beta. And that's what we define information in the weights. Okay. Of course, it depends on your choice of P and Q. So the prior and the code are your choice. And there are at least, oh, by the way, this has the form of an information bottleneck, for those of you who are familiar with Tali Tishby's work, except that D and W are not random variables. So this collapses to triviality if you think of it in terms of Shannon information, but it's perfectly well defined the way I've done so. So again, the information in the weights depends on how you measure it, so it depends on the choice of prior and posterior. There are at least two obvious choices. One is the uninformative prior, and that yields the Fisher information of the weights, which is a very natural notion for control theorists, because what you're doing is you're taking the discriminant, you're perturbing it, and seeing the effect on the output. If instead you imagine, if you could do that, averaging, so taking as a prior with respect to the weights, the average of the posteriors over all possible data sets that relate to the task, that would be a Shannon type of information. Now, Shannon you cannot compute. How do you average over all possible data sets? But if you could, that's the number you would get. Okay? So why do we even bother with Shannon information if it entails averaging over data sets, which we typically get 1? Well, because it is very important to generalization. And in fact, the Pak-Bayes bound tells you that the loss on the test set, assuming it's drawn from the same distribution of a training set, is bounded precisely by the information Lagrangian that I showed you earlier. Okay? Where this term reaches a minimum when you average with respect to all data sets. Okay? So this quantity, this Lagrangian, is what you would like your deep network to optimize. Right? It's the right thing for generalization. Unfortunately, the deep network only optimizes the first term, the empirical cross entropy. You don't have this explicit regularizer, but I'll come back to that. In fact, it turns out that you are optimizing this Lagrangian, even if you're not aware of it. Okay? So what matters here for the sufficiency of the representation of the test data, which is the test loss, is not the dimension, but the amount of information that the weights contain about the data set. Okay? Now, as I said at the beginning, who cares about the past? Okay? With the data set is sitting there, we'll never see it again. What we really want is we want to use it to learn a model that will allow us, given a test datum, to compute a representation Z that is ideally as informative as the data, so we don't throw away any information, and ideally invariant to nuisance variability affected data, but not relevant to the task. Okay, but how am I going to guarantee properties of representation of future data, given that I computed representation in the weights of past data? And it turns out that this is work of Alessandro Achille. There are two information bottlenecks involved in deep learning. One is the one I talked about, the weights, and the other one is the one of the activations, which relates to test data and network activation, as opposed to training data and weights. In theory, these two have nothing to do with each other, okay? But it turns out that for deep networks trained with SGD, one bounds the other. And so this is a deep learning result, not an information theory result. And specifically, the theorem is in one of the papers. If you minimize the Fisher information of the weights, okay, which SGD does, as I'll claim in a second, then you also minimize the Fisher information of the weights, and therefore you also minimize the Fisher information of the activations, even though they are a function of test data that you haven't seen. Okay? Now, if you minimize the information in the activation, a statistic that is minimally sufficient if and only if it's invariant, so then you achieve invariance to nuisance variability. Okay? So by looking for minimal sufficient representation of the weights, you obtain sufficient invariant representations of the activations. And this is really remarkable, I think, and this is one of the magics of deep networks, right? So now, as you may have seen, invariance relates to the Fisher information, but generalization relates to Shannon information. There is a gap between the two, and it's actually a wide gap. So it turns out that when you train a deep network with SGD, Fisher and Shannon go together, and that's another of the magics of deep networks, which you can prove. So I want to come back to the fact that deep networks do minimize the right Lagrangian, even though you're not aware of it. This is work of Pratik Chaudhary, who's sitting in the audience somewhere. And so there's a few equations here, but this is a control audience, so you're not afraid of them. So take the empirical cross-entropy loss. I'm just going to write it as the expectations of some function. And SGD is just a difference equation where you compute the gradient on a mini batch, and the residual, you think of it as noise. It's not really noise, but it has an associated diffusion matrix. You take that to the continuous limit, you get a stochastic differential equation. Associated to that, you have a Fokker-Planck operator that controls the evolution of the conditional density of the weights, now random variables, given the data set. And now you take, assume that there is a solution, you think of it as a variational solution of some optimization variation of functional. So there is an energy phi that you're minimizing, and then you look at what energy in the metric, in a particular metric, in this case Wasserstein, that corresponds to, and that corresponds to the minimizer of the JKO functional, which is well known to people in PDEs. And the JKO functional is the empirical loss you started with, which is unsurprising, but there's also this added entropic term that says that in order to find the correct solution, you actually want to add noise to decrease information, and this entropic term is precisely the information in the weights. Okay? So even though it's not there when you write your script for SGD, SGD puts it there for you, okay? Which is yet another magic of these deep networks. Okay, so the picture is roughly speaking like that. So you have weights that are function of the data set, which are data that's stored in the past, and you train them in such a way that minimizes the sufficiency term, the loss, but also at the same time minimizes the information term. So you want to add noise during your training, and that creates a bottleneck. It's not a dimensionality bottleneck. It's not a model reduction in the classical sense, but it's in the information sense. And by doing that, you can guarantee property of the activations, which are functions of future data. And these properties are sufficiency, so you minimize the loss, but also invariance to nuisance variability affecting future data. Okay? Okay, so I want to go back to Hubel and Wiesel. So remember this plot. This plot is now the Fisher information in the weights during training over SNET 18 on CFAR 10. Okay? And what you can see is during training, the information goes up and then comes down. And Fisher information is the curvature of the loss landscape around where you are. So you don't need to be at the global minimum for it to mean curvature. And so what it means is that as you're training, your network goes through some narrow bottlenecks or corridors. Okay, so the shape of the loss function is very complicated, and there are these trajectories, and you can actually show that if you run a nilde to zero, you have limit cycles, and Pratik Chaudhary showed that. But essentially, this picture shows that during learning, you have to traverse these bottlenecks. And these are irreversible dynamics. Once you traverse the bottleneck, you have no way of going back. Okay. So, as I said earlier, you can control noise, you can control information during the training process. You can do nothing, and then information is maximal, or you can inject noise, like crazy, and then information is destroyed, and in between, you have a knob per weight. It turns out you can actually feed this back and ask the network to learn the noise that is optimal. And the way you do that is quite simple. During the training process, you assume a prior for the weights. In this case, it's actually log normal for reasons that I won't have time to get into. And if this was Bernoulli, then this would be called dropout. If this was Gaussian, it would be called variational dropout. But more in general, you can choose whatever you want, and this is information dropout. So you literally control, in a feedback loop, the information that you feed back during the training process. Now, one of the favorite ways in which we use deep networks today is we train them on a task, let's say find cats and dogs in images, and then we use it for something else like finding tumors in a mammogram. And sometimes it works, sometimes it doesn't. And how do you know? Well, you try it and then see. Okay, so we'd like to be able to predict whether, given that you have trained for a particular task, and now we know how to do it in the sense that we know that the representation we learned is minimal, sufficient, invariant, how will you do in a different task? Or bets are off, right? So we'd like to know if we can, given the solution of a learning problem, which is a data set, or the weights of the representation trained to minimize the information Lagrangian for that data set, can I reach another set of weights? Okay, so imagine that you're in the loss landscape, you converge somewhere, there is a different task somewhere else, can you go from A to B? Okay, so in other words, we would like to introduce a topology in the space of tasks, being able to say, are two tasks close? Is training a network for finding cats and dogs closer to driving an autonomous vehicles or to reading a CT scan? Okay, so this is a very long story and long calculations, but basically we have an approximation of the probability connecting any two paths in any given instance of time in the loss landscape. So what is the probability of being able to go from a particular task represented by sets of weights W0 to another task represented by a set of weights WF between T0 and TF? This is done using Feynman's path integral approximation. And what comes out is, again, surprising because this probability factors into two things. One is a static term that only depends on where these solutions are in the loss landscape relative to one another. And this turns out to be the difference between the information in the weights the way I've defined it earlier. Okay, so it just comes out straight in the distance between tasks. But there is also this term, which is a dynamic term, it's a viscous term, it's a drag term, and it's a term that tells you that even if two tasks are very similar to each other, you may not be able to go from one another, okay? Because there's no high probability path between those. And this is real, okay? This term is not trivial, and you've seen it in critical periods, okay? So now we can measure distances between tasks and probability of going from one task to another. I have only 1 minute left, so I'll go fast, quick. So there is a static term of the task and a dynamic term of the task. We know how to compute efficiently the static part, and in fact, we can embed large set of tasks. This is a small picture, but every single dot there, there's 26,000, are a training of a deep network. And what you see on the left is a taxonomic tree. And so this distance reflects known taxonomies, but also keep in mind that there are tasks that are very similar to each other, same inputs, same outputs, slightly blurry in one case, critical periods, yet you cannot go from one to the other. So that's existence proof that the dynamic term is non-trivial. Okay, so I hope at least if you take one thing home is this picture that shows that during training information goes up first and then decreases, so you have to forget in order to learn. That's why I tell my wife that I'm still learning. And this happens while performance is going up, so you are still learning. And it's an intrinsically dynamic process. It can be controlled, and the question is how do you control it? And the theory of representations that we've been developing in the past 15 years answer some of these questions. And I think the meta point here that I like to do is that it's obvious that learning is useful for controls of dynamical system, but it's also true that dynamics and controls play a key role in learning. And even though most of the theory for deep learning focuses on the asymptotics, critical period experiment shows us that the transients are very important, and there's a lot to be understood there, and there's a very fertile ground for exploration. Thank you.
Questions or comments for Stefano? Sasha.
Sorry, common sense-wise, some of the things at the beginning didn't make much sense to me, because you said, okay, once you learn something, you cannot unlearn this. Well, of course, we know that if you have dynamical systems, they have if you optimize a function with multiple minimum, right? Then of course you can get stuck in their own local minimum, and you'll have difficulty returning back. But also, similar comment, to prevent such situations, people typically intentionally include forgetting factor in adaptation, in learning, so you forcefully forget the information that you got fast. So, I mean, on one hand, there is, yes, so in my view, there are some common sense explanations for things.
Right. So on the first issue so the simplest explanation is you're stuck in a local minimum, right? This is actually not the case, okay? So I'll explain this plot in 1 second. Keep in mind that in the critical period experiment, you start with a loss function, and then we switch to a different loss function. So if you're stuck in a minimum, which one it is? Is it the second one or the first one? Because there are two different loss functions, right? But it turns out that if you look at, so for instance, here's a plot of the two principal components one against each other after critical periods, you see that the solution actually moves, and moves quite a bit. It just moves in a way that doesn't help, okay? So it doesn't affect test loss. Now, yes, of course, you can take the learning rate, which is annealed here, either exponentially or piecewise constant, and you can reset it to the maximum. You can start fresh, and then you have zero memory of everything, and then you start from zero, of course. But here, the idea is that we do pre-training, and then we do fine-tuning. This is the way in which most deep learning works today. And you would think then training on classifying slightly blurring CFAR images would help you to then classify sharp CFAR images, but in fact, not only doesn't help you, it hurts you. You can never learn. You would be better off learning from scratch. I'm happy to elaborate offline.
Thank you very much. Fascinating results. I was wondering, in the 1990s, there was this literature on connectionism, people really trying to take this notion of development in neural networks seriously. And there were interesting papers by people like Jeff Ellman and so on the importance of starting small. Later on, there were papers also that were going to the other direction of learning the best first maybe doing a low-pass filtering of your inputs and then increasing the detail overall, and that had beneficial effects for learning. So I was wondering, how would you think are your results depending on the capacity of your networks and maybe dynamics in the capacity of these networks over time?
Okay, so your question pertains to lifelong learning or continual learning, and these results don't have any known implications to that, so the short answer is I don't know. But the second part of your question was in terms of capacity. The assumption that you need to make in all of these results is that you have sufficient capacity to overfit. So when you have the training loss, you can send that to 0, and that's typical of these deep networks. So the networks that I've discussed have in the order of 100, tens to hundreds, millions of parameters. These are not toy experiments, okay? And so they typically have sufficient capacity to overfit CFAR 10 or CFAR 100. So. But in terms of implications for continual learning, this is not yet. We're not there yet.
So we have one more question, I think, over there.
Yeah, I was just wondering, while training, can you monitor at which part of this curve you are? Like, you know that right now you're at this peak of information, or you have moved out of that?
Yeah, you can compute the feature during training, yes. Right.
So you could control or monitor that online in order to do some online kind of adaptation to that.
You can monitor and you can control it because you can inject however much noise you want. This is what comes out with training with SGD. This is not the case for. So this is closed loop.
Yeah. Okay, we have one final question.
Thank you very much. What implications do you have if you change the data? So let's say it will be very sensitive to the data you have trained your algorithm. And so what happens if, in a real autonomous scenario, you won't have any offline training, you'll just throw it outside, which would be the real autonomy. We'll throw it outside and then leave it do whatever you want.
That's right. Yeah, so especially for domain adaptation where you change the statistics of the data that you feed to the model. So there's two sides to the transfer learning story. One is when you change the output space. You train natural images on cats and dogs, and then you train natural images on pedestrians and cars. Okay. And then there's the one where you train the statistics of the input. You're doing it for electro-optical images, and you switch to infrared. So typically, fine-tuning doesn't work very well when you change the statistics, the low-level statistics. And the experimental critical period shows exactly that. And so the implication is that tasks that you intuitively think are very close to each other might not be. For instance, if you're driving and all of a sudden you switch IR camera on because you're at night, you would need to be careful about that. And so here's an example where you have a large data set of iNaturalist, materialist, and so you get classes to cluster together in this distance, which are not according to taxonomic distances that you would find intuitive sometimes. It's a form of robustness, I would say, more sensitivity than robustness. There's no equilibrium here, but yes.
Okay, good. Before we thank Stefano again, let me remind you that lunch is going to be served outside at the same time that the poster session. So kind of make sure you grab some food and talk to all our wonderful poster presenters. And we reconvene here at 2.